In the last lecture, we discussed the law of gravitation. We expressed the force between two particles due to gravitation in several ways in vector form. We also learned that the force of gravitation is a central force and is a conservative force, which means that if I move one particle from one position to another, the work done depends only on the distance and not on the path taken. In this lecture, we shall consider acceleration due to gravity and gravitational potential. The force due to gravity on a mass m placed on the surface of the earth is, as we have seen earlier also, equal to g times m into the mass of the earth divided by the square of the radius of the earth. And the direction in which this force acts towards the center of the earth is called the vertical direction. This is important to remember. If somebody asks you what is vertical force, your answer should be any direction which is pointing towards the center of the earth is the vertical direction. Wherever you are, vertical direction is the direction towards the center of the earth. This is important to remember. Now, the force is F, the mass of the particle is m. Therefore, according to the second law of Newton, there must be acceleration in the particle, and that acceleration is denoted by g, which is F by m, and which is equal to this. Ultimately, it is equal to g into the mass of the earth divided by the square of the earth's radius. And once again, to emphasize, this force or acceleration is in the vertical direction, that is, in the direction towards the center of the earth. It is always vertically downwards. Whether the particle is going up or coming down, the acceleration due to gravity is always vertically downwards. And if we plug the values, mass of the earth and radius of the earth and the value of g, which you remember was determined by Cavendish, and then we get the value of g, small g, acceleration due to gravity, which is equal to 9.81 meters per second square. For most purposes, we shall use g equal to 9.8 meters per second square. In fact, to make things easier, sometimes we will use g equal to 10 meters per second square. Like the gravitational force, the acceleration due to gravity must also be a vector quantity, and therefore, the vector g is equal to the vector f by the mass of the particle. The magnitude, however, is 9.81 meters per second square, as we have learned. And once again, to emphasize, the acceleration is always in the direction downwards, vertically downwards. The force mg exerted by the earth on a body of mass m is called its weight. Remember that weight is a force. Therefore, its unit is Newton or capital N. The value of g, however, is not constant and varies slightly on the surface of the earth from the equator to the poles. I shall show you in a minute. As a result, the weight also varies slightly over the surface of the earth, only slightly, not very much. Stating that my weight is 50 kilograms is erroneous. Although we use it every day, it is actually erroneous, is wrong. What we should say is that my weight is 490 newtons, because the weight is a force, therefore, we must use the units of force. However, kilogram weight is also a unit of force, and a kilogram weight produces acceleration of magnitude 9.8 meter per second square in a mass of 1 kilogram. However, in day-to-day conversation, we do not express the word weight. We simply say kilograms. As I said, my weight is 50 kilograms. What we should say is my weight is 50 kilograms weight, or 490 Newton. And here I show you a picture, and you can see the mass is expressed, or the weight is expressed in grams, whereas it should be actually in gram weight. Now, I told you that the value of acceleration due to gravity and therefore the weight varies from the equator to the pole. You can see why. The radius of the earth at the poles is slightly shorter than the radius of the earth at the equator, and therefore the acceleration due to gravity, being proportional to 1 by r squared, is slightly smaller at the equator than at the poles, and therefore the weight at the equator is slightly smaller than the weight at the pole, and it varies all over the earth, very only slightly. Variation in g with height. If we go outside the earth space, how does g vary? Let us look at this. The value of g at a point whose distance from the center of the earth is r is given by this. We have seen it several times now. So, at a height of r from the surface, which means 2r from the center of the earth, the value of g becomes g0 by 4. g0 is the value this g me by r squared. The value of g at the surface we call g0, and if we go to a distance 1r from the surface of the earth, that is 2r from the center of the earth, the value of g becomes g0 by 4. If we go to distance 2r from the surface of the earth, that is 3r from the center of the earth, then the value of g becomes g0 by 9. So, it varies inversely as square of the distance from the center of the earth. However, if height is not very large, it is very small compared with the radius of the earth, then we have a slightly different formula. We can write g as g times me by r plus h square, where h is the height from the surface. Therefore, r plus h is the distance from the center of the earth. So, we can write g as, we can take r squared outside, we can express 1 plus h by r squared, and if we use the binomial theorem, we can write g0 into 1 plus h by r raised to power minus 2, where g0 is g, capital G, into me by r squared. And now again we can expand binomially, because h is very small compared with r, and we get gh, that is the value of g at a height h from the surface of the earth, is equal to g0 into 1 minus 2h by r. At a height of 100 kilometers, for example, you can calculate gh would be 9.81 into 1 minus 200 by 6371, which is equal to 9.50 meter per second square. 6371 kilometers is the radius of the earth. Variation of g with depth, that is, if we go inside the earth, what happens to the value of g? We have seen that when we go above the surface of the earth, then the value of g decreases. Let us see what happens if we go inside the earth. Suppose we are at a depth h from the surface of the earth, that is, we are at a distance d from the center of the earth, that is, d plus h is equal to the radius of the earth. Now, we must find the value of g at a depth h. How do you find that? The first thing is to remember that the matter in this shell of depth h does not matter. We can prove it rigorously by mathematics, but physically we can think of the forces exerted by all the particles in the shell. Shell is this is shell, this lighter tone of depth h. Each particle in this shell attracts this particle, and all these forces will add up to 0. Therefore, we need not consider the mass of this shell. To get the value of g at depth h, we need to consider only the mass of this sphere of radius d, which is equal to r minus h. And now it is very simple. You assume that the earth is a uniform sphere, that means it has a radius r which is the same everywhere, and its density is rho, which is constant everywhere. Then we can write the mass of the earth as 4 pi by 3 rho d cubed, simple formula. This is the mass of, not of the earth, but of this sphere of radius d. So, 4 by 3 rho d cubed, and the acceleration at this point, which I denote by gd, is equal to g into m by d square, the usual formula. And if I put the value of m, then I get 4 pi by 3 rho g times d, and d, you remember, is the distance from the center of the earth. So, the value of g inside the earth at any point is directly proportional to the distance of this point from the center of the earth. It is proportional to d. So, it varies linearly with the distance from the center of the earth. Here I show you graphically what is happening. This axis shows acceleration due to gravity, and this axis shows the distance r from the center of the earth. This is the radius of the earth. So, up to this point, the value of g varies linearly, proportional to the distance from the center of the earth. But if we go from the surface of the earth above into space, then the value of g varies as 1 by r squared. So, from the center of the earth, the value of g varies linearly up to a distance r, and then from that point it varies as 1 by r squared. That is the value of g variation from the center of the earth. Remember that this value of g, the variation that we have considered, is on the assumption that the earth is a uniform sphere. The real earth is not a uniform sphere. You know, I have talked about the radius of the earth being slightly shorter at the poles than at the equator, but that is very small distance, very small difference. But if we go down, the density of the earth varies and increases as we go down. Actually, the earth has been divided into layers. It has a layered structure. There is a solid inner core, then there is a liquid outer core, and there is a solid mantle, and then there is a crust, which is a very thin layer. I have shown it slightly bigger just to show that it is there, but actually crust is about 20-25 kilometers depth. It is a very small distance compared with the radius of the earth. So, that is how the structure of the earth varies. So, it is not a uniform sphere. So, therefore, it must have some effect on the value of g. What is the effect? Let us see. If we go to the bottom of the outermost layer, that is crust, which is about 20 kilometers deep, then what happens? You see, this crust has very little mass. It is a very thin layer. It is very light density, very small density. Therefore, it has very small mass. So, the mass of the earth shown here in greener sphere, which is at the depth of the outermost layer, the change in the mass is not much. The mass of this sphere is almost equal to the mass of the earth. However, the change in radius is significant, because radius goes as 1 by r squared. Therefore, any small change in radius is significant. So, therefore, what happens is that although the mass does not change, the radius has decreased, therefore, the value of g increases. This is surprising. Let us see. What I have told you earlier is that the value of g increases from the center of the earth to the surface of the earth. Let me show you that. It increases from the center of the earth to the surface of the earth linearly. Now, I am telling you that because of the structure of the earth, the value of g actually increases to begin with. If we go to smaller depths, the value of g actually increases rather than decreasing. Why? Why does it happen? As I said, this sphere whose mass is neglected in calculating the value of g at a certain depth is very small. The change in radius is significant because g varies as 1 by r squared. Therefore, the value of g actually increases in the beginning. That is, if we go by this graph, it should not go like this, it should go like this. It should increase slightly and then maybe decrease. I will show you again. Here, a theoretical model of the earth's interior has been built by scientists studying the propagation of seismic waves through the earth. You know, these seismic waves are the waves produced at the time of earthquakes. Based on this model, the value of G has been calculated at various depths in the earth. This is the model calculation. We see that there is no decrease in G, and this is the result. This is the graph if we assume uniform sphere. This is the graph, the upper one, if we take the actual structure of the earth into account. So, the value of G increases slightly up to almost half the radius of the earth, and then it starts decreasing, becoming 0 at the center of the earth. So, what we are going to do is to take a unit mass from the point B to the point A in the gravitational field of the earth. You see, A is at a point distance r1 and B is a distance r2 from the center of the earth. And this work done from B to A is called the gravitational potential difference between these 2 points B and A. And if we use mathematics, then you know quickly, F is minus Gm by r square times r cap, and since dr from B to A is in the opposite direction to r cap, therefore, when we take F dot dr, we shall get, because this minus sign is then taken care of, and we get the potential difference equal to Gm integral from r2 to r1 of dr by r squared, and this is the integral. And if we bring the unit mass from infinity to a point at a distance r from the earth, then the work done is V equal to minus Gm by r. You can see if you take r2 to infinity, then this becomes minus Gm by r. This is called the gravitational potential at a distance r from the earth, and this is a scalar quantity, and therefore, this can be added, unlike the gravitational forces which have to be added vectorially. This is actually a general expression. If you take any mass m, then at a distance r from it, the potential is minus Gm by r. And you see, we are moving particle from infinity, where the gravitational force is 0, to a point near the earth. So, work is done from moving this particle from infinity to that point, and that work is the potential at a distance r. And it also means this, at infinity the potential is 0, near us the potential is minus. So, it is actually decreasing, the potential is decreasing. So, the particle is moving from a higher potential to a lower potential. Difference of potential, that is important, and not the potential at a point, because difference of potential tells us which way the mass particle would move. It moves from a higher potential to a lower potential, and the work done in moving from infinity is Gm by r for a unit mass. For mass m, it is equal to minus G small m into capital M by r, and this is known as the gravitational potential energy. That is the potential for unit mass. For mass m, this becomes the gravitational potential energy, minus G m by r. It is negative, remember. And here is a sketch of how the potential varies near the center of the earth or near any mass m. It is 0 at infinity, and then it decreases. It decreases sharply in the neighborhood of the mass m, and we say that there is a gravitational or a potential well, and a particle coming from infinity falls in that well. And if the particle falls in that well, then we need energy to get it out of that well. So, if we want to remove somebody or some particle from the center of near the earth to infinity, we will have to do work on it. And if the particle falls, it falls from higher potential to lower potential, and it loses potential energy, but it gains other forms of energy like kinetic energy. And if a particle falls, I will show you by this sketch. This is a normal star, and this is either a black hole or a neutron star which has a very strong gravitational field, and this strong gravitational field attracts particles from this star, and the particles go and fall in this gravitational potential well, and if they fall into the well, they lose potential energy but gain kinetic energy, for example, and they become very hot. Since they become very hot, they are in a position to emit even X-rays. And another sketch, the normal star, this is black hole or neutron star, and matter is falling. As it falls, it loses potential energy but gains kinetic energy, becomes very hot, and is able to emit X-rays. And therefore, wherever there are X-rays from a source which is not visible, we suspect that this is a black hole. This is how black holes are searched. In fact, we look at the signal of X-rays, look at the source. If we can see the source, fine. If we cannot, then we suspect that this is a black hole. So, we have seen that the potential energy of a mass m near a massive body of mass m is this. The negative sign indicates that mass m is bound to the massive body. Why is it bound? Because we need energy to set it free, therefore it is bound, and because work equivalent to minus gm m by r must be done on it to remove it to infinity, where it is free of the influence of gravitational field of m. An important thing that we did not say was that when a particle is brought from infinity to a certain point, there is no change in the kinetic energy of the particle. That is, all the work done goes into potential energy. In the next lecture, we shall take the topic of escape velocity. We shall see what is the minimum velocity that we must give a particle so that it can escape the gravitational field of the earth.